Greenhouse gases are the second most important thing on Earth making it habitable, the first being the magnetosphere. Without these two, we wouldn't have the liquid water necessary for the complex life we know. Nowadays, the amount of greenhouse gases in the atmosphere is too much for the life that currently lives here, and things are getting a bit hot. Cooling things down requires a lot of energy, but there's a way to do this with no energy input on our part. The greenhouse effect is named as such because of, well, greenhouses. The air temperature in an enclosed space underneath a glass plane will always be warmer than if it wasn't there. We've all experienced this when entering a car on a hot sunny day, so it feels intuitively obvious. But why does it happen? There are two ways heat transfers across interfaces. There is conduction, the physical collision of molecules and atoms transferring or absorbing kinetic energy. And there is radiation, the emittance and absorption of light. The majority of your personal relationship with temperature is in the form of radiation. So how does radiation influence temperature? Light is a property of oscillating charges. Whenever charged particles wiggle, they produce light. The inverse is also possible, and light can wiggle charged particles. Visible, ultraviolet, or what we call shortwave radiation, primarily wiggles the fast-moving electrons in the bonds of molecules and atoms. Infrared, microwave, or what we call long-wave radiation wiggles entire molecules. Electrons exist as complex wave functions that behave like particles. When two or more electrons are near each other, their waves interact or mix with one another. This mixing is itself a new wave function that oscillates, and because it is a mixing of charges, there exist regions of higher and lower densities for that particle or charge. It's this oscillation that can be influenced. You must have this dance of particles to absorb light. Dancing electrons are called an electron cloud. You can mix multiple electrons together to form electron clouds, and each electron cloud will have a specific frequency. To visualize this, I've mixed 3 out-of-frequency waves together. Right now it looks like a jumbled mess, but if we zoom out we can see that it starts to repeat. Therefore, we can think of this as our electron cloud oscillating. If we provide another wave at the same frequency, it will fundamentally alter or oscillate the electron cloud, and the electromagnetic field energy will be absorbed into the electron field. What does this mean for the greenhouse effect? Well, light from our sun is principally shortwave radiation. The electrons in glass, or the gases in our lower atmosphere, aren't dancing in the right manner to absorb this light. This shortwave radiation passes through and is then subsequently absorbed by the Earth, warming it up. Since all molecules, atoms, and particles are always dancing, the Earth itself is releasing light, but much weaker, in the form of long-wave or infrared radiation. These wavelengths are now too low a frequency to oscillate the electron clouds. However, they can oscillate entire molecules or ions. In most molecules, there exists slight variations in charges throughout them. Some regions will be more negative or positive than others. As our light wave passes through them, the oscillating electric field component can oscillate these charge imbalances. If this vibration is a correct frequency, then our entire molecule becomes vibrationally excited and the light energy is absorbed into the kinetic energy of this motion. I like to tell people to try to create a wave in a water bottle. You'll soon realize you need to move it back and forth a certain frequency for it to work. This is precisely what happens for greenhouse gases, except instead of a wave forming, our molecules become vibrationally excited. This vibration or motion of the excited molecule is heat. It can then transfer that heat to neighboring molecules via conduction, or it can simply radiate that absorbed light away in a random direction. In our atmosphere, the gases are too spread out to transfer their heat by conduction and thus will immediately radiate the light away. This is the property of the greenhouse effect. Instead of simply emitting the Earth's heat away into space, when our greenhouse gases absorb that light, there's roughly a 50% chance it will be re-emitted back to Earth. And if it is emitted away, it could still be absorbed by another molecule of that greenhouse gas, which then has another roughly 50% chance of emitting that light back to Earth. That is the beauty and mechanism of the greenhouse effect. An inverse greenhouse allows infrared light to pass right through, thus no potential to be returned to the Earth. Additionally, it blocks much of the radiation from the sun that was giving the Earth its warmth in the first place. As a result, the volume underneath an inverse greenhouse radiates away more energy than it receives and cools down. So what kind of material will do this? Infrared light is principally absorbed by molecules with charge imbalances and asymmetries. Simple polymers are kind of the opposite of this. They are simply long chains of hydrocarbons. Not only are there few charge imbalances to interact with the light, but even if they could, it's kind of hard to vibrate this large molecule. As a result, most plastics are transparent to infrared light. So plastics are a great starting place, but how can we make them reflect or scatter shortwave light? Researchers at MIT took advantage of a principle of light called me-scattering. Whenever light encounters a sphere made of dielectric material, a fancy word for insulators, the waves passing through interfere, causing destruction and scattering. When we think about light as a particle or a photon, these waves represent the probability of deflection. Although passing straight through is the most probable outcome, each photon has a certain likelihood of deflecting away. Therefore, if a material has thousands of spheres, then the likelihood of light passing through every single one is very low. This scattering effect is most prominent when the sphere has a similar size as the wavelength. So if this material had spheres with sizes similar to the shortwave radiation from the sun, then that light would be most strongly reflected. And that's precisely what the researchers in this paper did. Big thanks to Arnie Leroy for answering some of my questions on this and discussing the research in his field. Polyethylene, the most basic of plastics, can be filled with nanopores to form an aerogel. Each pore acts like a sphere and serves to scatter the incoming light. But that's not the main advantage of using an aerogel. With many infrared transparent coatings, although they do facilitate the inverse greenhouse effect, simple conduction, or what is referred to as parasitic heat gain, can permeate through them into the material they are supposed to insulate. Aerogel is extremely insulating. Thus, with its implementation, you get the benefits of its infrared transparency, as well as insulating against the surrounding heat. When this aerogel coating is layered on top of yet another infrared emitter designed for cooling, in certain circumstances the surface underneath can be over 10 degrees cooler than the surrounding ambient temperature during noon in the Atacama of Chile. What's exciting about all of this? It's estimated that 15% of electricity consumption and 10% of greenhouse gas emissions are ascribed to cooling systems. These percentages and gross values will certainly increase in the coming years. As a greater percentage of humanity shifts to electricity as their main source of power, the more we can reduce that consumption, the easier and stabler that transition will be. Finding methods to passively cool structures and buildings will be absolutely crucial, especially in regions where power supply isn't very reliable. Turns out this is an entire scientific field I wasn't even aware of. By installing manufactured inverse greenhouse panels on the roof of a building, not only do you reflect sunlight, you can also run water underneath carrying the ambient temperature from inside the building. This heat can then be radiated away. In very hot environments, the amount of energy radiated away in a day is almost double the amount of energy that would be absorbed by traditional solar panels. This is because it's not reliant on the light incidence angle and continues working at night. There is also research in developing infrared cooling fabrics. These two papers were released in the last 6 months and take two separate approaches. The first is a potentially convoluted metafabric which weaves polytetrafluoroethylene or Teflon nanobeads and nanofibers along with titanium oxide nanoparticles into polyacetic microfibers, which is essentially a bunch of scatterers suspended in an infrared transparent medium. The most impressive thing in this paper to me was, when used to cover a car, the covered car's interior was 30 degrees cooler than the uncovered cars. Personally, I'm intrigued by the possibility of its use in temporary constructions and shelters. Imagine tents in desert festivals or markets, where people can enter inside and actually feel cooler than the surroundings. The second paper wanted to implement this property into the ever-fashionable material silk. This was achieved by binding aluminum oxide to the silk fibers with tetrabutyl titanate. The main goal was to reduce silk's very strong ability to absorb ultraviolet light. The aluminum oxide particle diameter was chosen to reflect the ultraviolet light while still letting infrared light to pass through. According to this paper, the skin temperature of someone wearing nanoprocessed silk can be 10 degrees cooler than when wearing cotton. Kinda seems too good to be true, but those living in hot climates potentially won't have to choose between looking fresh or feeling fresh. I started this video with the ambition to teach a bit about the way light influences the world we live in, and ended up discovering a whole new field of material sciences. That's probably one of my favorite things about making these videos. Digging deeper into a topic always uncovers something equally or more interesting. And hopefully, what I find will inspire one of you to start your own research into a field presented in one of these videos. Either way, I want to thank you for sticking around as the channel grows and sharing my passion for the world around us.